Hey everybody, this is how to load and train our student model. So first of all, we start with knowledge distillation is the technique of distilling the knowledge of the teacher model to the student model by using the teacher model's outputs as soft labels for the student model's training. The soft labels are the probabilities or logits that the teacher model produces for each possible output, which contain more information than the hard labels, which are the actual outputs. This can help the student model learn from the teacher model's confidence and uncertainty. To load and train our student model using knowledge distillation, we need to do the following steps. First, we need to import the PyTorch library and its submodules. We've already done this in previous lectures by running the simple following code. Then, we import the Transformers library and its submodules. After we do that, we import the Hugging Face datasets library. Next, we import the Distilbert model and the tokenizer from the Transformers library. Then we import the PyTorch pruning module. Then we load our fine-tuned BERT model from our output directory that we made previously, followed by loading our pre-trained Distilbert model from the Transformers library, which we'll use as our student model that we want to train using knowledge distillation. We can load it by running the following code. Next, we want to load our dataset. So we load our SST2 dataset from the Hugging Face datasets library. We've already done this in the previous lecture by running this following code. Then we pre-process our dataset by using our tokenizer to encode the text and labels into tensors that can be fed into our models. Hopefully this becomes a little bit repetitive for you guys at this point. That's kind of the goal, is to, so you can get at least kind of that, these first parts of it will become repetitive. Then we define a custom loss function that combines the cross-entropy loss and the Kullback-Leibler divergence loss. The cross-entropy loss is the standard loss function for classification tasks, which measures the difference between the predicted labels and the true labels. The Kullback-Leibler divergence loss is a measure of how much information is lost when using one distribution to approximate another, which in our case measures the difference between the teacher model's output and the student model's outputs. We can define this loss function by running the following code. Next, we define a custom training step function that takes a batch of data and returns a dictionary of metrics. The function will use our training model and our student model to compute their outputs on the batch of data. The function we also use our custom loss function to compute the loss on the batch of data. The function will also use an optimizer to update the parameters of our student model based on the gradients of the loss. We can define this function by running the following code. Next, we define an optimizer by using the AtomW class from the PyTorch library. The optimizer is a tool that updates the parameters of our model based on the gradients of the loss. We'll use the AtomW as our optimizer, which is a variant of the atom that has a weight decay regularization. We can define it by running the simple following code. Next, we train our student model by looping through each batch of data in our dataset and calling our custom training step function. We'll also print some statistics such as the epoch number, batch number, loss, and accuracy at regular intervals. We can train our student model by running the following code. Once this is completed, these are the steps that we need to load and train our student model using knowledge distillation. In the next lecture, we'll learn how to evaluate our student model after training. See you in the next lecture.